of your model, process model. Okay. Indeed, the properties, okay, it means properties. It's not improved. It is not only contains the thermal models you are going to select, but also in the property packages, they are for each model you select. In addition to, you are selecting what's the thermal model you apply, and also you can see how this package model the transport properties or thermophysical properties, such as the density, viscosity, surface tension, and diffusivity, etc. for the system of interest. Okay. So before you choose what's the package or what is the model you are going to apply, you have to define what are the components in your system. Okay. So after you have a well-defined for the properties for your system, and then you move to the simulation panel and then develop your process flow sheet. Okay. So we are here at property, and then you can see the setup here. Okay. Okay, the setup here basically tells you the unit set you are going to use the metric, okay, as the unit. And then the calculation options or unit setup, unit set. And basically you don't need to do the modifications, okay? And also you can see there is a blue, okay, there is no red sign in the setup. That means these folders basically is okay for you. And you have to move to the folders which shows you the red sign, okay, such as component. And in our demonstrations, we will use carbon dioxide and methanol binary system as the model development demonstrations. Okay, so here is the place we are going to define component. We can use find, okay, and then it pops up a panel, and you can key in the name of the component, such as carbon dioxide, and then find now. Okay, and then you got a result here. Okay, so you double click it, and then you can see in your back your main screens, and the carbon dioxide is already in the list, and then you use the methanol. Okay, find now. So if you key in the methanol as the name, it shows you a lot of components that contains methanol. So you have to find out which is the one you would like to choose in your system. Okay. In addition to the component name here, you can also check the, for example, the molecule weight here, and the boiling point here, and also the case number here. Okay, So be sure the one you select is what you want. Okay, no, just, do you want, do you want to replace the component A with B or add methanol to list? We choose add. And then, okay, so now you have carbon dioxide and methanol. And then you can, for the component ID, for the abbreviations, you can, oops. You have to close it, and then you can do some modification on this. So you can revise the name as CO2, and then the X if you want to delete or replace it. You just want to rename. And then methanol we use NEOH and rename. Okay. So here is our system, just a binary system. So are you all with me?
Yep.
Okay. And then after you define a component here, there is no red sign here, so you can move to the method here. Okay, that's the most important part for the properties. So for the method, you jump into the red sign here, specifications. Okay, that's wonderful. So first, it shows the property method and options. Okay, and this is the method filters, and you can see the default one is common. Okay, that means the common a general system. Okay, not specified to polymer, not specified to electrolytes, not specified to chemicals. Okay, so you just stay with this, that will be fine. And for the base method, okay, it shows you a lot of abbreviations such as BK10, Chelsea, CPA, ELEC, NRTL, ENRTL RK, and ENRTL XR or NRTL or ideal. Okay, so each method, okay, stands for a package, but it only uses the abbreviations of the thermal model as the method name. Okay, so in other words, if you choose, for example, an ideal, okay, if your mouse is in the ideal, you can see that it shows the ideal property method, and then use Raoult's law and Henry's law. Okay, and you can move to the NRTL, and it shows you that they use the NRTL model with ideal gas and Henry's law, or NRCL set and PC set. If you choose, okay, the one Penrod, that's the Penrod-Nielsen equation of state, and indeed, that's here. And when you, please be reminded that when you choose this method, you are basically calculate the non-ideality of the system using equation of state method, and they use a single equation of state, Penrod, to estimate the stochastic coefficient of a component in vapor phase and liquid phase. It also calls find method. Okay. So okay, so you can see the panel on the right. Okay, if we select modify here, and they are asking you if you want to really modify it, you say yes. and then you are able to see the detail of the model. So this one, EOS, that's the equation of state. So if you see the description, it tells you that Penn-Robinson equation of state with original literature alpha function, and this model has built-in binary parameters and is used in Penrod property method. So do you remember that in our in this week in our lectures we tell you that when you are developing a thermal model, indeed, when you are report your thermal model, you have to also report the parameters you apply, because the parameters differs from systems to systems. So again, if you look into the description, it shows you the model has built-in binary parameters. Okay, despite you don't know what are the parameters yet, but it's fine. And then you can see the details. Okay, so for the EOS, in the EOS options, you can see a lot of abbreviations, and it basically tells you that you can choose Penn-Robinson equation of state with different mixing rules, such as PXRK mixing rule or MHV2 mixing rule, or with Wang and Sandler mixing rule, blah blah blah, etc. So I just want to tell you that an equation of state, if you apply an equation of state to represent a binary system, you have to apply mixing rule. Okay, the mixing rule assumes the fluid, the mixture is a hypothetic fluid. So if you choose to use different mixing rules, indeed you are having different, you are developing different models, indeed. But for your project here in this semester, you probably need to stay with the original default. Okay, so you don't have to do anything. And I just tell you that you have a lot of options. And then let's see okay. So for the liquid gamma here, and you cannot choose or you cannot modify, because if you choose Penrod and you are using equation of state, okay, so you don't need to specify the gamma function to calculate the activity coefficients. But okay, let's do this. If you choose the NRTL, for example, and then you still click the modify option, and for this model, it allows you to choose the vapor phase equation of state and also the activity coefficient model, and they are ESIG, that means equation of state ideal case, and the liquid gamma is GM Reynolds, that's gamma model Reynolds, developed by Reynolds. Okay, so okay, if you choose activity coefficient models, you have to not only specify an activity coefficient model, but also a fugacity coefficient. I mean, an equation of state to estimate the fugacity coefficient. But for equation of state models, you don't need to specify the activity coefficients. That's for your reference. And here, they also shows you how to estimate the liquid molar volume and also the liquid molar enthalpy For example, the liquid mixture molar volume is calculated using Rocket model. And the liquid molar volume, indeed, that relates your density. Okay, that relates the estimation of your solution or mixture densities. So here is some options you can choose. But in our demonstration here, we will use Penrod. Okay. So, okay, after you choose Penrod, and then there is still some red sign below the method here. Okay. So the red sign appears in the parameters, and then see the binary interactions. Okay. And then there is only one red sign here, that's PRKBV-1. Again, PRKBV-1. And if you jump into the this folder, you can see they have component I, component J. They stand for the CO2 and methanol binary. And they give you the source, the Aspen EN or EOS LIT, and the KIJ parameters here is 0.023. Okay, that's the default parameters. Okay, so basically you can stay with the default parameters. Okay, in our demonstration, we will see how these default parameters perform against, specifically that's the model result against the data.